This video is about quadratic functions and their graphs. We're going to specify two commonly used forms of this, or for quadratic functions, though their names are not necessarily used across the board the same way. So, for instance, some authors may call something vertex form, and that form is given as f of x equals a times the quantity x minus h, in parentheses, squared, plus k. Now, the reason this is sometimes called vertex form is that it shows you the vertex of the graph of this function in what's already set up. So the vertex is the point h comma k, where h and k come from this vertex form that we have spelled out here previously. Now, if a is greater than 0, meaning if it's positive, then what we get is a parabola, is the name of this shape. It's kind of somewhere between a V and a U shape. And if a is positive, it opens upward. So you'll have a couple branches that have arrows on the ends of them pointing upward. If a is negative or less than 0, it opens downward. So you have it just kind of flipped upside down, pointing downward. Now, another form is sometimes called standard form, and this one reads as f of x equals ax squared plus bx plus c. That's a very typical setup we've been seeing for quadratic expressions and equations lately. In this form, you can still find the vertex. It's just not as simple as it is in vertex form. So for the vertex in this standard form, the x-coordinate of it will amount to the expression negative b over 2a, again, where those a, b, and c values are just a and b, and that expression come from the standard format here, ax squared plus bx plus c. And then the y-coordinate of the vertex would be found simply by plugging in the x-coordinate that you had maybe just found as negative b over 2a into the function for x. So like f of negative b over 2a. That's possibly a little bit of arithmetic, maybe assisted by a calculator, but you're plugging in the x-coordinate for x in the function to find the y-coordinate. Now, just like with vertex form, if a, the leading coefficient here, is positive, then we get a parabola that's opening upward. If a is negative, of course, it's a parabola opening downward. Now, let's talk about some steps for graphing in either form. They're slightly different, but there's a lot of similarity. What we're going to do first is find the vertex and plot it. Obviously, if you're in vertex form, that's pretty quick. In standard form, maybe a little work involved, but we still want to know what the vertex is. Or secondly, we can find the intercepts or other points to plot and connect to draw a parabola. Sometimes the standard form we've written above here is more convenient for finding intercepts because typically if it's factorable, you can spot it in that form, factor it, and then you can set those equal to 0 to find the intercept. So there's pros and cons to using either form, but we'll practice trying to use both of them. Speaking of which, let's go ahead and try to do an example where we graph and then also list the domain and range in interval notation of the following function. It's given as f of x equals, then we have the quantity x minus 3 in parentheses, all squared, and then plus 2. So probably a good first step would be to figure out which form your function is given in. As you can tell, if you just do a simple comparison with what we have written above, this is in vertex form. If you were to imagine lining this up with the vertex form we have above, we would say a times x minus h all squared plus k, if you can kind of think of it in terms of that. So you can kind of line things up and say, oh, okay, so h happens to be 3. Of course, a is 1. We should specify that as well. So a is positive 1 because you see nothing out in front of the parentheses. So there must be an invisible factor of 1 there. And then, of course, k on the end there would be a positive 2. Observe that the h value we spotted of 3 actually turns out to be the opposite of the number you see inside the parentheses, right? We had x minus 3. You might typically say, oh, there's a negative 3 there. right? But the h value is the opposite of that. So in this case, it's a positive 3. And that goes to the fact that the formula, the vertex form we've written above, already has the negative sign built into it. So just keep that in mind. But then the k value is the same as whatever you're seeing in the problem. So there was a plus 2 on the end, so k is just a positive 2. All right, now if we know that we're in vertex form and we know the values for the vertex, why don't we start plotting this graph by understanding the vertex to be the point, remember it's h comma k, so that'd be 3 comma 2, given the values of this function. So we can go ahead and just plot a point at 3 comma 2 on our graph, knowing that that's the vertex. Now, let's also keep in mind that since a is 1, as we've already identified, remember, the sign of a, whether it's positive or negative, will determine which way this graph opens. It's either opening upward or downward, and as you can tell from our notes above, when a is positive, we get a parabola that's going to open upward. So that just gives us a quick little visual expectation for what this graph is. But we want more than just a vertex and then a curve, swooping through it in the right direction. We want at least another set of points. Remember, sometimes we can use intercepts and sometimes we can just use other points. When you already know the vertex, it's usually easy just to throw in a quick xy table, or in this case, f of x table, and then pick an x value close to where that vertex already exists. So since our vertex had an x coordinate of 3, for example, let me just pick 2 for an x value in this table. That means I'm going to plug x as 2 into our function to figure out what the f of x value is. When you plug in 2 for x, you get 2 minus 3 is negative 1. Squaring that will give you 1, and then add 2 for that last part at the end there to get an output, or an f of x value of 3. So when x is 2, f of 2 is 3, which means the point 2 comma 3 is on our graph. So let's go ahead and plot that. X is 2, y is 3. It's close to the vertex, but not right on it. And now, the nice thing about parabolas is that they are what's called symmetric. And what that means is once you have the vertex plotted, which we do here, you know that there is a line of symmetry that will always go right through the vertex. So in the case of this example, it's going to be a vertical line, and this has a name. Some books call it the axis of symmetry. And it's that way because the graph is symmetric about this line. Now, the value of knowing that a parabola is symmetric means that whatever you see on one side of the axis of symmetry will copy itself on the opposite side. So if we have a point at 2 comma 3 as we've just plotted, we know that as far as that point is away from the axis of symmetry, which would be just 1 unit, there must be a point that same distance on the opposite side of that axis of symmetry. So that means we already know there's a point at 4 comma 3, even without having to go through and crunch out the math to make the table. We know just based on symmetry there must be a point there. Now with 3 points, including the vertex, it's possible to graph our parabola. Since we know it opens upward and we know it goes through all these 3 points, we can at this point just go ahead and sketch it, just roughly enough, going through all those things so that it's a parabola opening upward. In this case, the vertex is down here in quadrant 1 as we have already plotted, and that's our graph. Now, part of this problem above also asked us to list out the domain and the range of this graph. You'll notice that the domain pertains to x values and the range pertains to y values. We've done that in context with other graphs before. So x values would be left and right, and because of the arrows on the ends of this parabola, which yes are pointing upward, but they're veering slightly to the left and slightly to the right as they do, if those go on forever, we would have to say our domain is all real numbers, which we'll write as negative infinity comma positive infinity. And then for the range, we could say, well, the vertex is the lowest point. It goes no lower than that. So for the range, we use that value of positive 2, the y-coordinate of the vertex. That's the lowest point, comma, the highest point would just be infinity, which means it goes up forever, given those arrows, and that would be our domain and range using interval notation. Now, we mentioned above in our instructions that sometimes it's helpful to graph the intercepts, and in vertex form, sometimes that's not the most convenient thing to do, but I just want to do a quick little exercise on what would happen with this problem if we attempted to graph any x intercepts. So let's say we didn't know what that would be, but we wanted to try it out. You could take your function and set it equal to 0. That's like setting the y value equal to 0. So that would be 0 equals, and then we have x minus 3 squared in parentheses there plus 2. Okay, but if you subtract 2 from both sides, you'd end up with negative 2 equals x minus 3 in parentheses squared. But notice here that if you were to try to solve this for x by taking the square root of both sides, you end up with a square root of negative 2. Yes, we know how to do an imaginary number to represent that, but imaginary numbers don't show up on the real coordinate plane that we're using to graph here. So that would actually have no solution, which means there are no intercepts, and sure enough, that's how our graph turned out. I just wanted to point that out in context. Sometimes you'd have a graph that does have intercepts, sometimes not. But either way, you could find them by setting the y value or the f of x value equal to 0 and solving. All right, let's try another example. Our second one is given as the function f of x equals 2x squared minus 7x minus 4. Now, you should be able to spot quickly that this function is in what we called above standard form. It's not in vertex form. That doesn't mean we cannot find the vertex. It just means it's not staring us in the face the way that this one is written. And so we're going to go ahead and use what we have written above as the formula to find the vertex. And so let's spell this out here. To find the vertex, remember x equals negative b over 2a, as we have written above. So for this problem, that would mean, of course, b is given as negative 7 in this original. So that would be like a positive 7. Negative 7 is positive 7 over 2 times a is 2. Okay, so really 7/4 must be the x-coordinate of our vertex. Now, to find the y-coordinate, of course, or the f of x coordinate, we'll say f of 7/4. We're plugging our x value in. And that you could do by hand or with a calculator. It's going to be approximated here as, well, the exact answer would be negative 81 over 8. Okay, so that you could find by hand just plugging in 7/4 to this equation originally there for x. But of course, that's going to be kind of a pain to graph. So we're going to approximate that as negative 10.1 just to put on our graph more easily here. Negative 10.1 we'll say. So we'll go ahead and call our vertex here what we've found, which is 7/4 for the x-coordinate. Of course, you could even write that as a decimal point, anticipating the fact that we're getting to a graph here. 7/4 is 1 3/4, which you could just say is 1.75. In fact, let's write that above just to be clear. 1.75. It's just easier to plot sometimes a decimal than it is a nasty improper fraction on a graph like this. So we have 1.75 for our x-coordinate. We've already estimated at negative 10.1 for the y-coordinate. That's our vertex. We'll go ahead and plot that. We'll have to estimate a little bit, of course, on this graph, but 1.75 and then negative 10.1 is going to be somewhere, actually a little bit off the grid that we have specified here, down in quadrant 4. Now, that's the vertex. Also note that since a here is 2, that's a positive value, we're expecting a graph that opens upward, a parabola opening upward. Now, that's nice, but remember, we want to find more points than just the vertex, knowing that it opens upward. Given the way that this function is written in standard form, let's see if we can find some intercepts. We've mentioned that above in our instructions, and I'd like to go ahead and walk through that process here. To find an intercept, to find an x-intercept, you would set y to 0. Well, y is like f of x, so I'm going to rewrite this as 0 equals 2x squared minus 7x minus 4. And then we want to solve this to find out what x would be. Well, This may be factorable. Of course, we could go ahead and try any factoring method we know to do that. It turns out I think this one will work as 2x plus 1 and then x minus 4. So pick your favorite three-term trinomial factoring method to go for on that one. And then using the zero product property, we'll set each of these factors to 0, which would give us an x value of -1/2 and an x value of 4, which means those are the locations of the x-intercepts. Okay, so we can go ahead and just plot points on those locations, so 4, 0 and -1/2, 0. So we can tell now that this graph is going to be fairly narrow. It goes through all three of these points, opening upward, which is useful for us to be able to graph this. We could now go ahead and actually just do it by connecting them. With a narrow graph, it can be a little tricky to draw it nicely. So the point is just be true to what's already true of this graph as we've specified. And then let's go ahead and write out our domain and range. Domain is x values for any parabola that's opening upward or downward. The domain should be all real numbers for reasons we explained in that previous example. They go on forever. And then the range, now this one had a vertex, as we've spotted here, with a y value of negative. We estimated it as -10.1 for the purpose of graphing. It was actually -81/8. Okay, so we're going to go ahead and use that value as the lowest. So I'll use a bracket since we actually get there with the vertex point. And we have -81/8 as that lowest point. And then it goes up forever, so comma infinity. And that will give us our domain and range. Of course, you could also find the y-intercept fairly easily here. We wouldn't absolutely need it to be able to graph this, but we could find it. Remember, for a y-intercept, you would set x equal to 0, and given that this function is written in standard form, it's pretty easy to plug in 0 for x. The first two terms would turn into 0. You'd be left with just the -4 in the end. So 0, -4 would be the y-intercept. Now, you could also go further, which would be unnecessary, but using the line of symmetry, which you know has an x-coordinate of 1.75 or 7/4, you could use that symmetry to say, well, how far is my point 0, -4, the y-intercept, away from that line? And then I could go that far on the other side as well to get another point. So like 1.75 is how far that would be away. Of course, if you double that, you get 3.5, and that's where the other point would be. But it's unnecessary to go through that much detail. Once you have at least 3 points plotted, including the vertex and a couple others, it's good enough to graph the parabola. Let's move on to another example. This one says graph using transformations. So this is a type of graphing that we've done in previous topics, which we're now going to kind of recall and apply to some parabola or quadratic functions. Now, the parent function for any quadratic, as we've seen, is listed as y equals x squared. That's the simple parent function. Our first example that we'd like to graph using transformations is given as f of x equals the quantity x minus 3 in parentheses squared plus 2. So we're going to have to go through and spot or identify what these So let's identify and recall that when you see x minus 3 inside the parentheses of this quadratic, that minus 3 means we actually are going to move things right 3 units. And then the plus 2 at the end, that would move things up 2 units. So this is the language of transformations. Of course, this function is given in vertex form, and so that's useful as well to understand as we've been discussing above. But let's go ahead and do a couple things with the graph now. Let's go ahead and graph the parent function with a dashed curve. So as we know, the parent function for a parabola goes through 0, 0, 1, 1, and -1, 1. And then also 2, 4, and -2, 4. And of course many others, but that's enough to get a pretty clear understanding of what that parent parabola function graph looks like. We'll graph that one first. And then we'll go ahead and understand what these transformations do. To go right 3 and up 2, that would happen with every point on this graph. So if we even just take the 5 points we've plotted and move them all right 3 up 2, according to those transformations. So this gives us several points. Again, they should all look symmetrical and producing the same shape as our original parent function. But then we'll just go ahead and connect them with a parabola shape to get the transformed graph that is now moved. So every point moves according to the transformations, producing this new graph. Let's try another example, still within these instructions of graphing using transformations. This next one is given as g of x equals x squared minus 2x plus 1. So you'll notice, of course, that this is in standard form, not vertex form. And you can go ahead and go, we've done an example above about using standard form. You can find the vertex with the x coordinate negative b over 2a, and then plug that in to get the y coordinate. Okay, there's a lot you can do to go through that. But I'd like to go maybe a slightly different route, just as an example here. Let's take this one and put in vertex form. So we know what vertex form is, and we've seen how useful it can be. When given a function in standard form, you actually can put it in vertex form. And sometimes you have to complete the square to do it, but in other times, such as in this one, you can simply factor. This is actually a perfect square, which could be factored into x minus 1 in parentheses squared. If that's the case, of course, this is in vertex form with the h value of 1 and a k value of 0, which means that can point to how, or where the vertex is, but then also using transformations, you could say that this one would go 1 to the right, since it's x minus 1, and it wouldn't go up or down at all, so we'll just shift this thing 1 right. Of course, the standard parent function, as we've seen, is the basic parabola going through the origin, points 1, 1, negative 1, 1, and then 2, 4, and negative 2, 4. If we graph that one in a dotted or dashed curve, then we can take all of those points, move them right 1, and produce the final graph that we'd like given this equation, and that will look the same except shifted to the right 1. And of course, when you shift things, sometimes the domain and range are affected, and sometimes they are not. With any parabola, that's a function opening upward or downward, when you shift it up, as we did with the first example here above, you can see that the range would be changed because you're now using positive 2 as the lowest value as opposed to 0 in the parent function. So the range and domain do sometimes change with transformations or transforming a parent function. Just depends on how it's transformed. Let's continue in this topic with some extra application here of quadratics, and we'll do that with a definition. And we'll say this: the y-coordinate of the vertex, yes, the same vertex we've been talking about above, is either a maximum value or a max value if the parabola opens downward, which we've already said it happens when a is negative, the leading coefficient. But it's a minimum value if the parabola opens upward, which of course happens if a is positive. Okay, so same characteristics of a quadratic function, but now we're just putting some extra application and meaning on the vertex in these cases. So those are, of course, applicable above. If you look at our graphs, they all had either a maximum or a minimum. Actually, these were all minimums because they were opening upward. But of course, if it were a parabola opening downward, you would look at the vertex and say, oh, the y value of it is the maximum value. In our cases above, it was the minimum value. And there's really nothing different than we've done already in those graphs to find the vertex. But I want to go through and show another skill, which is using a graphing calculator to find a minimum or maximum value. Now, we have an equation or a function given here, a quadratic function. It's given as y equals 2x squared minus 5x minus 7. As already seen above, we could use what we already know of standard form, which is what this one's in, to find its vertex. which matters if you're trying to find the minimum or maximum value. Now, given the fact that the a value is 2, let's just kind of note this for a second. If a is 2, that's a positive leading coefficient, which means we would expect a parabola that's opening upward, which means we would expect the vertex at the bottom of it, which means we're expecting a minimum for this function. Okay, so again, you could go through all of the negative b over 2a kind of stuff to find it, but I want to also walk through this one using a graphing calculator. If you turn on your TI-84 Plus graphing calculator, and then go to the equation editor, which is the top left button that says y equals, you can clear out whatever you might have in there. I'll just pick on the first y1 equals for our equation. We want to type in this function in its given standard form, so we'll go ahead and punch those numbers in. So we have 2 and then x squared, so x squared using all the typical buttons we're used to on a graphing calculator, minus 5x, and then minus 7, so that we now have our function typed in the y1 equation editor window. Now, you may be used to using a table or a graph. We could take a look at this graph just to make sure everything's making sense by hitting the zoom button, and then either zoom 4 or zoom 6 is a nice standard square kind of window. I'll just pick on zoom 6 for now. Zoom 4 is zoomed in a little bit more, but zoom 6 should be good enough. You can see in the screen once hitting that there's a parabola opening upward, as we already suspected would happen. But notice you can't quite see, or maybe we can see it, but it's just barely cut off in the zoom 6 window, the bottom of this parabola where we're expecting to find the vertex. Now, we're interested in that vertex because we want to know the min or max of this function. Of course, we know that's going to be a minimum at the bottom of the vertex there, or the bottom of the parabola. We want to know what those coordinates are, though. So, though you could go the algebraic root of negative b over 2a for x and then plug that value in for x to find the y coordinate, I want to demonstrate how a calculator can find those values just the same. And to do so, we actually want to change our window a little bit so we can clearly see where that vertex is and not even suspect that it's being cut off, as our zoom 6 window may have done. So let's change the window by hitting the window button, which is kind of underneath your screen here. And then we want to go to the y min value and just expand it a little bit. The y min is set at negative 10 when you use zoom 6. We're going to change that. It doesn't have to be drastically different. Let's make it negative 15. Maybe even a negative 12 would be fine enough. But if I change that to be negative 15, that'll expand the window downward a little bit so I can see more clearly. Now let's go ahead and hit the graph button again. Not zoom 6. We already did that. That would reset the window again. We've adjusted the window, and now if I hit just the graph button, it'll take me back to the newly adjusted window. Notice you can see it kind of just took our window down a little bit, so now we can clearly see the vertex of our parabola here. Now, to find the coordinates of the vertex, we're going to do as follows. We're going to hit the second button and then the trace button, which above it says calc. That's the menu we're using with the second key. So second, then the trace button, which says calc. And then we want to use one of these functions. Notice we already know that this is going to be a minimum value given the way the parabola opens. So we're going to use option 3, which says minimum. And of course, we'll select that by hitting enter. It takes us back to the graph with a cursor on it now that will move if you hit the left and right arrows in your calculator. And that cursor will follow the curvature of the graph as it goes. And then it produces the coordinates of that cursor at the bottom of the screen as you move it. So you can see the x and y values of that cursor changing as you move it around. But notice there's a little question in the bottom left corner as well. It says left bound question mark. Okay, so what the calculator is asking for is a little bit of a hint. How can we tell it a little bit more closely where this minimum is approximately? Well, the left bound means we have to go to the left of where we know the minimum value is, but we want to get close to it in the process. So I'm going to go use your arrows to go down to where you know you are to the left of the vertex for sure. And you can tell by kind of moving your cursor left and right a little bit to make sure you're to the left of it. but then also make sure you're clearly to the left of it. And then we're going to hit the Enter key, which will supply that value as the left bound for the calculator. It just needs a little hint on where to look. Now, once you hit Enter, the question changes, and now it's asking for a right bound. So now you're going to use your right arrow to scroll with the cursor past where the vertex is. And by the way, you may say, well, why don't we just put the cursor on the vertex and use that? Well, the cursor may not actually hit the vertex. It's giving you approximated values every few decimal coordinates or so, and it might not actually hit the vertex. So we're going to scroll to the right until we pass the vertex. You know you have if your y coordinates start increasing, because of course the function's going back up after the vertex, now to the right side of it. Once you get over there to the right, for the right bound, you'll want to hit Enter again. And when you hit Enter over there, that should now lock that value in for the calculator. But then the question changes to guess. Now it wants a guess. So we're going to go back and scroll down to where we think the bottom of this parabola is using the cursor. And once we get there, we're going to click the Enter key again. And this time it's going to lock that guess value in for us. But the guess isn't actually what we want. It will think through that for a second and give us out the minimum value. Now the read that I'm getting on this calculator gives us the x coordinate of the minimum as 1.2500003. Okay, so it's rounding these values, but they're usually good enough for our purposes, so we're going to go ahead and take those for now. So we'll end up rounding the x value given to be 1.25. The the 4 zeros and then a 3 following that, matter, but they'll be insignificant in the long run. So we'll just round it to 1.25. And the y coordinate given, notice it only has 3 decimal place values, so it's probably not rounded and doesn't need to be, which means we'll use negative 10.125 for the y value. Now, that gives us, from the calculator, that gives us the minimum value, but in context, from what we now understand about parabolas, that minimum value, of course, was the coordinates of the vertex. And again, you could find those coordinates in the exact form using the negative b over 2a for x, and then plugging that in to find the y. But this is good enough for us. So if it said find the min or max, we can say the minimum is actually the y coordinate of the vertex. So let me relabel this a little bit more clearly here. So this point that we found is actually the vertex, right? We just discussed that. But the minimum value of our parabola happens to be the y value. So in this case, negative 10.125. That's the y coordinate of the vertex as specified above. That means that would be the minimum value because this opens upward and the vertex is at the bottom of the graph. Now let's finish this topic off with an application or a word problem. Using what we now know, this one says you have 200 feet of fencing to enclose a rectangular plot that borders on a river. Okay, so I think it's good to get a picture going on here. So let's just kind of draw some kind of river, and then we have a rectangular plot or field bordering it, so kind of beside the river there. We'll draw a rectangle for it, and that'll help guide our labeling here. If you do not fence the side along the river, okay, find the length and the width of the plot that will maximize the area. Okay, there is our key phrase. We want to maximize the area, and then what is the largest area that can be enclosed? Well, let's first label this diagram according to what was said. We know we only have 200 feet of fencing total, so we could come up with some labels to help put that together. Any rectangle will have opposite sides equal. If I call the, let's say, bottom of this rectangle x, then of course the opposite side would also be x. Now the other side, okay, the other two sides are the river and then the longer side of this rectangle, fence. But if I call that other side y, I have another variable to deal with, and that might be more annoying than useful. So we're going to go ahead and use what we know of the limitations in this problem to label that other side still using an x. notice we only have 200 feet of fence to use. Well, if we've already used X and X for these two top and bottom sides, then the other side with the remaining fence must be 200 minus 2x. We've already used x here and x there, that's 2x. Take that away from 200, that's how much is left for that other side. So 200 minus 2x is how we could label it. Now, we want to maximize the area, which means we'd like to create a function to represent it. So why do we say this? For a rectangle, let's recall area equals length times width. Okay, but we're going to use a more algebraic function definition. We're going to call this a of x because we can write the area in terms of x's. And length times width would end up in this example being x times 200 minus 2x in parentheses. That's just multiplying length times width of this rectangle. Of course, that's a little obscure at this point. Let's go ahead and distribute the x to make it look maybe a little more familiar. So we'll say here a of x equals 200x minus 2x squared. Now, we might feel a little more comfortable if we rearrange and put that in descending order, in which case we would have negative 2x squared plus 200x, and then it's maybe more familiar to know, aha, that's actually a parabola in standard form. Notice that the a value being negative 2, let's write this out here, so a is negative 2. If a is negative, we know it opens downward. If it opens downward, the vertex is at the top, which of course would represent the location of the maximum of the function, which is exactly what we're trying to do here. We're trying to maximize the area. We have the area now represented by a quadratic parabola function, and so this is all making sense. Now, we want to find those coordinates. Notice this question being asked actually has two parts. The first part says find the length and width of the plot that would maximize the area. Well, the length and width, as we have them labeled, are both in terms of x, which means we can use what we know from standard form of a parabola above to find that x value. Remember, x is equal to negative b over 2a. If you think of this parabola in standard form, we've already said a is negative 2, b would be this 200, and then of course c is 0. You could think of a plus 0 on the end. We don't really need to write it. I mean, you could, but you don't have to. And so if b is 200, then we can plug in here to get the x-coordinate of our vertex to be negative 200, that's negative b, all over 2 times a. Well, a was negative 2. So 2 times negative 2. Okay, so this is negative 200 over negative 4. That turns out to be 50. All right, so what that's telling us is that the x-coordinate of this vertex has to be 50. And then, of course, the y-coordinate of it would be found by us plugging in 50. So that'd be like a of 50. And you can just plug in 50 for x in this function. You'll end up getting 5,000. Now, this question had two parts. The first part was find the length and width that will maximize the area. Well, when we found x as 50, then we can find the length and width. So let's call this the dimensions for maximum area. That would be x, which is 50, and the units should have been in feet, I believe. And that's just one of the sides, the x side. The other side was 200 minus 2x. Well, again, if x is 50, then 2x is 100. 200 minus 100 would be 100. So that means 50 feet by 100 feet would be the dimensions of maximal area for this field. That was one of the questions. The other question was, what is the max area? So we computed that here just a second ago as 5,000. So we can say 5,000, and then it would be feet squared. That's max area. And then really we should say max dimensions are given as the 50 by 100 feet.